Okay, today is 8.3, day 2. And this is the slide that is, telling us about what we're doing for today. And there's some solving of some kind of strange exponent or exponential kind of equations. But I want to remind you what we did before, which is on Friday, since it's been a couple of days at least. Let's talk about it. All right. First, if you were going to solve this top one, I gave you two options. One was to take the log on both sides. You go add a log into the situation. Log 4 to the x, log 2 to the 3x minus 1. But that's base 10. Couldn't we be more strategic? Do you remember which one? Log base 2 was a pretty good idea. Do you get log base 4 would also work pretty well because on the left side it would just equal x. You get that? Because this and this are the same. The answer is just x over here. Log base 4 would have been good, but I think log base 2 is actually the best. But so the point is you can take the log on both sides. Just be strategic about which one you pick. Because see, this one now, that works perfectly. Those tell you that the answer to this whole right side is just 3x minus 1. All right, so if we do it that way, then don't forget that this can drop down in front of the problem then. The power can go down in front. That's called the power rule. So if I have log base 3 of anything, actually, these don't even have to match. If I have a 2 there, it can drop down in front and be like that instead. Okay, so that's a quick reminder of how you can take logs on both sides. So next, when we get to odd solving, odd as in weird things you have to be able to solve. This top one brings up a topic called use substitution. This is something you're going to use in calculus someday. You're going to use it a lot. We're just going to kind of give you an intro to it today. And what it means is, what if I could take out part of this problem that makes it difficult? Like, do you get if it wasn't e to the x, if it was just x? And if this e to the x was just an x, then it would just be x squared plus 5x equals negative 6. That's a quadratic. You just set it equal to 0. And then if you can factor it, you should. Do you get from there? It'd be pretty easy. All right. But this problem isn't that easy. But you can substitute and make it that easy. Watch. I say let u equal e to the x. I'm saying let's take out e to the x and put in u. Then I will have u squared plus 5u equals negative 6. Now I can just add 6 to both sides. If you can factor it, you should. Oh, it's 2 and 3. And now my answers are, just to ignore this for a moment, u equals negative 2 and u equals negative 3. There, solved it. But it's sort of sidestepping the original question. Do you get we never even dealt with the e of x? We just took it out. So now what do you think we have to do now? Put it back in. Because u is actually equal to e to the x, now this problem becomes e to the x equals negative 2. And over here, e to the x equals negative 3. And the especially wicked part about this one is that now when you actually solve it, you got to do a conversion, a rewrite, I've called them. You rewrite this thing into a log. It's log base e of negative 2. What's wrong with that? Can't have a negative there. That's the argument. I can't have an argument that's a negative. So, no solution. Now let's try the other side. Maybe this one will work out. Log base e, sorry, of negative 3 equals x, and that one didn't work either. That was a particularly tough one. All right, so let me give you a more normal one. See if you could solve this one by pulling out the complicated part and putting in something easy. And I always recommend u, because that's what they're going to do in calculus. It's kind of a standard thing. Whenever you do a substitution, you put in a u, because it's kind of an underused variable. All right, so try this one. E to the 2x. Again, you'll pull out the e to the x and put in a u. Plus 3 e to the x minus 4 equals 0. Do a u substitution like I just showed you to solve this one all the way down. And this time, there's actually a solution that actually works at the end. I'll pause for a second while you give that one a try. Let's see how you did. First off, how many of you actually remembered to write let u equal e to the x? Because if you didn't give yourself mathematical permission to do that. You got to put that on the side. That's your only way of being okay with just totally changing this problem to u squared plus 3u, u squared plus 3u minus 4 equals 0, and then it factors to u plus 4 and u minus 1. Did I get that right? I think so. And then I get x equals negative 4, or u equals negative 4, and u equals positive 1. And then I make this one now. If you have a u left at the end, you know something's wrong. Get it? Because you did a u substitution, and e to the x is what you actually should have. E to the x equals negative 4, and e to the x equals 1. This one simplifies down to impossible. How many of you got no solution on that side? Awesome. Because log base e of negative 4 doesn't work. And this side, log base e of 1 equals x. And how many of you took the last step to know that you won the argument and you have x equals 0 as your answer? Good. That's what you should have said. Because you do know log base e of 1. It's just 0. And if I actually needed to prove it, my life's on the line, I got to know this is actually right. If I stick in a 0 here and here, it turns out that this becomes, anything to the 0 is 1. This becomes 3 times 1. 1 plus 3 minus 4 is 0. It worked. Cool. Okay. That's called a u substitution. It's very powerful and not easy to do. It's not that hard once you understand it, but I get it's a really long. I mean, look at that. It just goes on and on and on. It involves rewrites, all kinds of stuff. All right, so let's look at another kind of question that you have to know for today. What's the difference between this and anything we've ever done before? It's got greater than. So what's the difference? Actually, not much. Just act like this says equals and then tell me the answer. What's the answer? X equals 3. But then, as you can imagine, you're not done. Do you remember me saying that when you have a greater than sign or a less than sign, you should think of it like the tip of a number line, like the pointy end of a number line. That reminds you, ooh, I should do a number line and put 3 on it. Now, does 3 actually work? 3 does make it equal 8, but does 8 bigger than 8? Doesn't actually work. Empty spot. If it had said or equal to, then we would have filled it in. You remember that? Okay. So then, where's something bigger than that I should test, like 4? Put in 2 to the 4th. Is that bigger than 8? Yes, it is. So it works. How about something smaller than 3, like 2? 2 to the 2nd is 4. That's not bigger than 8. Those things don't work. There we go. Could you rewrite it? Does 3 to infinity? Sure, if you wanted to. You don't have to, though. All right, so what's different about this? It just, you don't know what the answer is. It's not like 3. So what do you put? What is the answer? Without using a calculator, log base 2 of 5 is what x is. And that's what you put on the number line. I get you don't know what it is, but you write log base 2 of 5. Now it's good to kind of get perspective a little bit. That means if I put in 2 here, that would be a little too small, so it's probably like 2.4 or something. So whatever it is, let's say it's like 2.4. I take numbers bigger than that, I try them, turns out they're bigger. So they work, and the things on the other side don't, and so the only difference is we don't know what this is, and we leave it that way. Why? Because I don't want you to have to get your calculators out, and I want you to get used to you won't have a calculator for the test. So you can't just like graph both sides and see where they cross. That would have actually worked again. Graph this, graph that, see where they cross, crosses to some decimal. Boop, that's the answer. All right, this one, you have to get this clump alone first. What's the first step? Divide by 10. And then you get 15 divided by 10 comes out nice. What decimal? 1.5. Now it's 2 to the x is greater than 1.5, and it would be just like all the others. You'd leave your answer in log form because I don't want you to use the calculator. And I see an end of a number line here, right there. That reminds me I should make a number line. Put that important number like right here, and shade on one side over the other. All right, that's enough on those. This kind, the part 3, that's just a reminder to, if you're going to use a calculator, what are you going to do? Graph both sides. See where they cross. All right. And that would tell you your answer. And you could do this at the calculator super quick. Zip, zip. You find out it's like, 4.3. And then, 4.3 is important. And then hopefully you remember the rest of the steps, just like all the other ones. Test things on both sides. All right. So I want to actually do a few with you here. Just to start your homework. It's day 2 right here. And so let's look. Number 25. Do you get this has not nice bases to try to make the bases the same? Do you remember the technique then? Log of both sides. So I'm going to rewrite it here. And if I take a log base, what? Well, you pick. You pick a logical base to do. Just remember you got to do the same thing to both sides. And remember also that you can get the x out of here by bringing it down to the front. Or the x minus 1, bring it down to the front. All right. Now, 34. Do you see the tip of a number line laying there? Yes, I do. And I don't know what that answer is, so I'm not going to ever know it. I'll figure out that it's ln, log base e, of 53. And then you just got to test intervals on both sides. You might be like, well, what do you mean? I don't even know what this is. We'll pick a really big number then, like 100. If you put e to the 100, do you think it's bigger than 53? Yep, probably. All right. Here you got to get the clump alone. Then you might just want to do a rewrite because you only have a power on one side, so you don't have to do logs on both sides. You can if you want. All right, moving on. 36 and 37 are similar. A lot of rewriting going on. Remember, when they get tough, rewrite them. Then, because we have a big lab to do in class today, I'm excusing the whole rest of the assignment, all the pages after this too. You just have to do up to 37. All right, now this is important. I know some of you are going to be tempted to go try to do your homework right now because you're really efficient and you don't have much time and stuff. But I need to teach you something that you'll need for the lab, okay? So I'd like you to put your iPads down and take that piece of paper that I had you get out and use something to write with and the blank piece of paper that you have out. You don't need to borrow from a friend, do it. Be prepared to write upon said paper. Grab a pencil. Need to borrow one? Okay. Here's the first thing. You need to get a general form for exponentials. Write this one down. Y equals y sub 0 times 2 to the power of kt. Write it. Staring at it won't help. All right, now, anybody want to guess where the starting amount goes for an exponential like this? Y 0. 0 is often used for like original or at time 0, which is like when you start. So that's the start. And then hopefully you'd logically know that that's the end. What you started with goes in y 0. What you end with is in regular y. And then what do you think t usually stands for in things like this? Time. It is. Or if it's like us and we're doing something with M&Ms today, it's the trial. Like trial 1, we do it once. I do it again, that's 2. I do it the third time, that's T3. Time 3, third time I did it. Does that make sense? Okay, now, the K is the thing that's a constant that depends on the situation. Do you get if I start with something and I end with something? If I'm going to always use a 2 here, which you can, I know a lot of people think you've got to be given that number. Nope. The 2 does mean doubling by itself, but what if I put 2 to the second power? That really means it's quadrupling. You see what I mean? Depends on the situation. Situation might call for it to be not doubling, but maybe it's tripling. So then I could put 2 to the what power would make it triple? 2 to the 1.5 equal to 3? 2 to the what is equal to 3? All right, I just did there. Okay. Anyway, that K depends on the problem. And that's what you're going to figure out today in this lab. So you're going to start with a bunch of M&Ms in a cup. Okay? How many you get depends on your group. I am not counting them out for you. Okay? You wouldn't want me touching all your M&Ms anyways, because you might want to eat them, but that's up to you. I have to say, my best recommendation for safety is that you just throw them away. But many kids decide to overrule me on this and eat them. It's your call. All right? I've been careful to keep them safe in the bag, and I've always used hand sanitizer before I take the little Dixie cup and dip it in there and give you your M&Ms, and they're clean Dixie cups each time. But from there, what you do with them, I don't know. I've seen kids shove them up their nose before, so you just be cognizant, decide for yourself. All right, so anyway, if you start with, let's say, 40 M&Ms, do you get how it's shaping up so far? I've started with 40. Okay, let's say you get 40 in your cup. You probably get more like 60 or something, but let's say you get like 40. Then you dump them out on the table, and that's why you have that clean piece of paper, because you don't want them touching the desktop, okay? And then let's say if you drop them from a distance, they're going to skitter all over the place. Just be careful. Don't be dumb here. Drop them out on the table. Do you know that M&Ms only have the M on one side? All right. So that means some of them, the M will be up, and some of them, they won't. The M's that are up go back in the cup. It rhymes, and I'm telling you, it's the most #1 question I keep getting over and over again, is so which ones do the M's that are up go back in the cup? And do you agree that these are started out in the cup, right? So then the only fair comparison is not to take the ones that aren't in the cup, but the ones that go back in the cup go here. Do you get if I am typical, I'm going to get like 20, but in the real world it isn't so clean? Do you get that sometimes you're going to get extra lucky and have more M&Ms that turn up with the M up and I get like 23? You get what I'm saying? All right. So at this point, you can solve for K. You might be saying, "No, you can't because you don't know what t is." Oh, you do. What's t? How many trials did we do? So therefore t is 1. It gets a little more complicated on the next one, because now you know we've got 23 M&Ms in the cup. There's two ways you can go from here. You can either say there's 23 M&Ms in the cup when I started the next trial, and then t would be a certain way, and then it got down to, let's say, 11 the next time that came out from my 23 in the cup, and I dump them out. The ones that are up go back in the cup. Do you get how this person changed the starting amount to be a new starting amount? That's okay. Here's the other way so kids sometimes do it. Same exact start, 23 equals 40 times 2 to the kt, but this person says, no, I want the original amount to stay the same each time, because I originally had 40, and now I'm down to 11. It's not like this is wrong. It's just you use a different t. All right. Now, do you get it depends, when I'm solving this, how many actually happen to come up, and I can't control that, and so my numbers might be off from the kid sitting next to me. If you're in the same group and using the same data, you'll get the same numbers. But I mean, some groups are going to get extra lucky on how many M's are up, and their numbers will be slightly different. But do you get if we average them, it all should come out about the same as long as probabilities aren't broken in the world? Think about it. Shouldn't the probability somehow turn out to be about 50-50 or about 0.5 that the M's are coming up? Okay, but hopefully you'll understand once you know what K is and you average it and you look at this and go, oh, it makes sense to me that K is this, because it'll all come together, I hope. For some of you, you won't ever have it come together, but at minimum, what you need to walk out with today is, if you had nothing else but this, we started with 45, and now when we went down to 22, and then we went down to 11, and then we went down to 6, and then we went down to 2, and then we went down to 2 again, because they keep rolling them, they keep coming up. You see what I'm saying? Do you get why I'm going to have you throw out the last few? Because even though we had an extra trial, it didn't even go down, and that's going to be way off compared to what it's supposed to be. All right, so I'm going to ask you to do the first 4 trials are the only ones that really matter. After that, it gets to be, you might have the same M&M rolled like 5 times before it finally comes up, or stops coming up. The M&Ms that are up are going back in the cup. What about the M&Ms that are down? They go flush them down. Very good. All right. All right, any last questions? Remember, if you walk out here with only this data, you can figure out the rest of the math later. But you got other people who are motivated to solve this right here, right now. So maybe, like, typically about 1/3 of the kids walked out of here and they already knew what K was. They had solved it 2 different ways and they were like, yep, got it. K's got to be this. Don't expect it to come out to something nice like, you know, -4. It's going to come out to some weird decimal like 0.943, okay? But it'll be really close to a number that will make sense if you understand probability. Okay, so this is the part where you'll need a group of 4, and I'm going to stop the video at this part. From here, they just roll them as I described. And if you're having to do this at home, grab some M&Ms, start with about, 45, 50 of them, and you can do the experiment at home. Take your own data. That's all I got for today.